Um, Before we get started, just wanted to get a quick understanding of how many of you here are involved with Yang modeling, design of Yang modeling, creating um, yeah, Yang for service packages. So quick question. So what are the most common parameters you kind of consider as your key parameters when you define your Yang models? So when you define a Yang model, what do you typically consider as a key parameter? Sure. Yeah, device names, interface names, right? These are pretty typical key parameters. What if you don't know the device name or the device or the interface that you're going to be using NSO to configure on? Right. How do you translate the intent of your request uh, uh, into actions that NSO can operate on? Um, how do you address without knowing the device name? How do you get identify the security vulnerabilities with with your request based on the intent without knowing the name of the devices? Yeah, the answer to all of that is intent-based network analysis and we'll examine that for a firewall automation use case. So before we get started, let's quickly look at the agenda. So let's take a quick look. So we'll spell out the perimeter security firewall automation use case. Um, and once we spell that out, we'll then paint a picture of the intent-based firewall automation journey. Talk about list out the benefits of intent-based networking, objectives of network path analysis, while looking at the solution overview of a path analysis platform, along with its interoperability with NSO. We'll go over some platform of path analysis, go over some of the features, talk briefly about OpenConfig, and finally wrap it up with a demo. Let's dive right into the scenario of a perimeter security firewall management use case. Enterprises typically offers several services to their customers and trading partners through various applications that are hosted in their data centers. These data centers are bound by firewalls, typically the lower bound and the upper bound firewalls uh, that abut the perimeters of their data centers. These are typically multi-vendor firewalls which enforce the perimeter of the data center or the network zones that they represent. Every incoming request to consume these applications that are hosted in various data centers are being vetted by these firewalls, come what you call as the border police that enforce the perimeter of these network zones. So it is a typical security practice to classify risks associated with requests based on the zone of its genesis. Uh, Requests that are originating from internet are typically categorized as critical risk. Uh, the requests that are spawned from like DMZ or from intranet, they are categorized as high, while those originating from management network are termed to be low risk, along with those from the production network. Hopefully, we have the context for the use case before we look at the overall journey for intent-based firewall automation. Typically, the firewall perimeter security firewall request commence with end user submission of rules to obtain access to certain applications and services via a firewall ticketing UI. Subsequently, the security engineers uh, uh, categorize work to vet these requests, um, to evaluate them based on a static listing of Excel spreadsheet, uh, to categorize them into the criticality based on a pre-canned list of IP addresses. After manually waiting out these IP addresses, they attach a categorization to the incoming request, and the request classification kind of drives what configuration would be attached as we go through the service configuration eventually. And then the firewall engineers go through the process of rule engineering, which is a RDS task with manual uh, path, path discovery. How many of you have done show trace routes, show CDP neighbors, show pings to get the path, go from one firewall to another to another? So they go through this RDS route of determining the path, and then eventually also go through policy optimization to do object group creations and eliminate duplicate rules. Um, so subsequent to that, like how many of you are involved with midnight fun with maintenance windows and weekend funs with maintenance windows, pushing in applications over the weekend, trying to get it to production? So some of those with implementation activities are like pre-checks, staging through the week, and then pushing the changes into the production environment during the maintenance window, and then doing a UAT, user acceptance testing, in order to verify whether it sages the business intent of the request, and then do a manual rollback. So as you can see, working through the midnight maintenance window, the security engineer and the firewall engineers, they are holding a grumpy look on their faces. What we can accomplish end-to-end intent-based firewall automation if we are able to translate the intent of the request and validate the security vulnerability based on the zones that these requests are going to be transiting dynamically, instead of using a static uh, IP addresses based listing. And if it can be bolstered further by using an automated discovery using the path analysis platform, as well as optimization, policy optimization, I think we should be able to obtain an end-to-end intent-based firewall automation. And as we know, NSO is probably one of the popular platforms for implementation and production push, and for carrying out rollbacks based on either cumulative rollbacks or based on filtering if needed. And if we are able to use fusion of BPA, which is powered um, by Forward Networks and NSO, we are able to obtain end-to-end automation, wherein like the requester submits the request through the BPA UI. The security risk assessment happens dynamically based on the zones that are representing the request path, and then the firewall engineer is able to validate or peer review and go through the RDS rule engineering process by using the path analysis platform, and then accentuate that by using the NSO platform for doing pre-checks via live status exec APIs, staging using commit dry runs, commit no networking, commit no deploy, and then subsequently go through the production implementation using the commit or service redeploys. With that said, so let's go over some highlights of intent-based network analysis here. So integration of current network state and configs into topology diagrams, enablement of analytics and search engines to quickly isolate potential security vulnerabilities, reduce the complexity of management of fire and maintenance of firewall policies, and crafting rules that are to be placed on network based on network path analysis. For the purpose of this discussion, let's go focus on the last bullet item here, which is to evaluate the path based on network path analysis. primary objective of network path analysis is to determine all possible paths between a given source and destination. We find out the list of devices, firewalls involved that NSO shall perform service configuration on upon at a later stage. Uh, so we can query the metadata reflecting the security zones of each device, identify the security vulnerability associated with each path of traversal, um, determine the ACL rules that are placed on all the firewalls in the determined path. Additionally, also get get the L3 routing, NAT, static route, and ARP configuration. So we would have device config templates for each of these device config templates within NSO for each of these aspects listed here. So the idea behind this solution for path analysis is to treat this as a mathematical problem. A non-mathematical problem would consider individual packets without its context, would not be able to reason about the whole network behavior, um, because they don't have the space of all packets in reference. So treating it as a mathematical model in our approach, path-based, in our path analysis approach, helps us consider the overall prism of the incoming packets, how it enters, where all it can go, how it can reach the destination, and what is the return path. And we'll see a demo of this this architecture towards the end. But the overall the sequence is, so we have a listing of all the devices, firewalls at the dynamic state routing table. So the data is garnered by the data collector from switches, routers, these firewalls, and replica of the entire network is maintained in data model, which includes the device models and network models. And then there is a proprietary algorithm which kind of transposes that, loads that into a topology tree or a topology database. Eventually, we are able to establish every possible network path based on the current config, states, and the adjacency list. And then we would have these custom apps which are kind of built, which would within BPA, which would facilitate search, verifying, predicting, and running some API requests. So using the path analysis platform to represent the device network configuration and the state table at a specific point of time, collector will, like I mentioned earlier, collector will collect the configuration and the network state information, create a network topology, and there will be a proprietary algorithm that forward uses that would run the algorithm to calculate the traffic path in the entire network. This process can take a few minutes to hours, depending upon the size of network, number of firewalls in reference, and the complexity of your network. And then we expose that, and there are multiple flavors through which you can capture or that you can consume the data that's been formulated, namely GraphQL. We'll talk a little later about GraphQL, REST API, standardized OpenConfig. We'll briefly talk about OpenConfig towards the end as well. So these through one of these different avenues, the data can be ingested into NSO's data model and then can later be used for service configuration. Or if you have your business processes which are very closely intertwined with some aspects of it in its workflow, you can let the business process automation platform drive the overall queries as needed in the workflow. So let's understand briefly about how this path analysis platform is able to generate the network topology. It collects data, a device configuration and states from each device using the IP address. It establishes what we call as adjacency list for every device using collected LLDP, CDP information. It identifies, defines subnets, routing tables, and the network paths. It's able to extrapolate live, up-to-date network topology diagrams. It's able to index and automatically create your network diagram with details about topology of the environment. It's able to visualize the network-wide L2, L3, L4 state of the network and all device configuration. You can think of it to be very akin to a Google search. How does a Google search work? Right? Like you have all these websites, Google's crawler engine, offline synchronizes all this and loads it into its proprietary database. It lets you, when you do a keyword search, it kind of retrieves it from the cache or the from the from the data that it has in its in-house proprietary database. Similarly, you can think of it from for network for firewalls. What's happening here is, as an offline process, the data collector is able to garner all the data based on the routing table, based on OSPF, BGP protocols. It's able to consume all that and ingest that into its proprietary database, transform that, treat that as a mathematical model, transform that, and superimpose that into a topology tree, and then it provides a API for the topology database to be consumed. Like we saw in the previous slide, it can be consumed using GraphQL, REST API, or OpenConfig based standardized models. Let's take a glimpse of how the path analysis platform facilitates search over the generated network topology. It searches across the network for the state, the behavior, and the configuration using query languages. It finds out the devices on the network, including its connection and its forwarding behavior, performs complete end-to-end analysis across the network. So custom apps can be built on BPA, whose business logic would be embedded within underlying BPA microservice. So integration with custom apps to show the network paths, the status of the policy checks, custom metadata attached to the network, and it can be representing the various security zones that we saw earlier, and it can be updated into the topology database. GraphQL, just to let you know, GraphQL was initially developed by Facebook back in 2012, primarily for internal usage, to let them retrieve the number of levels of or number of levels or depth of nodes to search, and then it turned into an open source project back in 2015. And it's pretty flexible in the way in which we can query, because it lets the client application decide what it is needing, or what it is looking for, without having to get what the API provides you and having to parse later. Let's understand how path analysis performs this path selection from multiple possible paths. So when it analyzes L2 through L4 network services, the security policies across end-to-end paths, including the host, firewalls, and load balancers, it connects a source and a destination address. It looks at all allowed paths through a network that match the policy of a search query. Using path selection algorithms, a path can be selected among several devices in transit. So it exposes. So if you click on the path, as you can see, so when you want to go from node X to node Y, you can see multiple paths. So in the diagram here in reference is showing that there are 32 different paths that are possible. And if you select one based on the path selection algorithm, if you're able to zero in on one of them, you can click on each one of them. You can look at the sample packet. You can look at the ACL config there. You can look at the NAT. You can look at the static configuration. And all these configuration details are exposed at a node level selected from the traffic flow in reference here. So we are also able to see the routing, static, and the NAT configuration here, along with the ACL rules. So let's take a look at a sample query um, over the formulated topology database using GraphQL. So when we started this session, we were talking about the devices, right? Like the device name or the interface name. These are the primary fields that we use as key parameters. So as you can see, as a client application, building a client application, we can have a structure a query such that we are looking for the device name, we are looking for the interfaces, we are looking for some other aspects of it. Let's say zone is a custom metadata here. We're looking for the zone adjacency list along with other aspects such as the access list, NATing configuration, static route configuration. Let's take a look at the sample GraphQL query response to this query over the topology database. As you can see, the zone is intranet, which kind of would tell us that it is a high risk based on the example that we saw in the first set of slides. And then it also retrieves details about the interface name, the operational status, along with the access list and the NATing configuration. So how does this modeling happen into the topology tree or the database in this path analysis platform? State tables, the space of packets and its forwarding behaviors are modeled into the custom data schema in this platform, similar to how Google does that for search queries and loads it into its custom schema and has a way to transform that and expose that based on a keyword based search. We can carry out searches, which we will see in the demo towards the end, carry out searches based on our source IP address, destination IP address, get all possible paths to be listed. And it's possible based on, so as we can see, the physical interface, the logical interface, these are listed and they get transposed into a custom data model schema there, which the path analysis platform uses, and that has correspondence to the various attributes. So before let's briefly discuss about OpenConfig. How many of you here have known about or worked with OpenConfig before? Okay, okay. OpenConfig are pretty much like a standardized Yang model ecosystem espoused by Google, Facebook, Apple, and along with other telcos. OpenConfig is more like a informal working group trying to head towards IETF standards. Not there yet, but trying to evolve towards more programmable infrastructure based on SDN principles by using Yang model driven management and operations. It's a consistent set of vendor neutral data models written in Yang based on actual operational needs and use cases and requirements from multiple network operators. You can go to it's a public GitHub. You can go to you can join the community if you have some use cases which are not being saged by some of the open config standards. You can provide your recommendations. You can join the community, and it is an evolving platform. They are trying to lead this into a more IETF based standards the near future, so that there is a more standardized approach with some of these Yang models. So some of these data models will eventually be supported natively on the hardware and the software platforms. So there are two flavors of OpenConfig modules. One is the OpenConfig with the generic type, which has more extensive use across multiple vendors, multiple vendor network elements, and multiple device types. And then there are extensions which are custom, specific to certain use cases, certain domains, and they are encompassed within the OpenConfig extensions module. OpenConfig. Let's just briefly talk about the generic type definitions which are encompassed within the OpenConfig type modules. They are the OpenConfig BGP policy to allow policies to utilize BGP specific routing attributes. OpenConfig interface for capturing the configuration and state of device interfaces along with their IP addresses, local routing for capturing the configuration on operational states relating to static routes. We saw a lot of static route examples in the image previously. Policy to allow particular matching routing elements and actions to be performed on the firewall policies. VLAN to capture configuration and state retrieval of parameters that correspond to VLAN on devices. So let's go ahead and take a quick look. Let's delve into the underlying bulwark of the path analysis app, which that resides within the BPA platform. So let's take a look uh, at the Forward Networks UI. So I'm gonna shift to my browser. Okay. So trying to locate the browser here. It is. Okay. I'm going to be logging into the platform. Um, so in just a minute. So in reality, in production, when we have the solution in production, we don't have to be logging into this platform because the data that we retrieve, that we query, is going to be so closely intertwined with with either the business processes, the workflows, or with the service configuration within NSO. So typically, we would be having a programmatic invocation of some of the data, but just for the demo purpose here, I'm going to just go over how to illustrate how these can be retrieved. So I'm trying to log into the platform here. Oops, bad password. So okay. So just a quick check, right? So we said like in order for us to begin, what was the first step? So we saw the architecture diagram earlier, right? So what was the first step for us to begin the path analysis? Like in the case of a Google search, there's a collection that is happening. So there is a data collection that's the prerequisite step in order for us to make these queries, in order for us to know about these policies. The first thing that we would need to know is to capture all the data that is loaded. So let's go look at the collector here. So typically this collector is like equivalent to a Google crawler, wherein like this has to be enabled for it to be able to go gather data from the network. So we have a collector, so we can add a collector. In this case, I have a collector here. Typically, we would go into this based on what type of operating system the collector is going to be loaded on. We would download a package for this one. I'm not going to do that. I have a collector um, that is uh, that is connected, and you can schedule the collector to say whether you want to have a custom schedule or you want it to auto collect. So do you want it to run daily? Do you want it to run on a nightly basis, on a weekly basis? And then you can schedule that. How often do you want the collector to collect? And there are different ways in which the collector can happen. Do you want to collect data from all your firewalls, create a snapshot at all times, or do you want a full snapshot at all times, or do you want to do a partial snapshot at all time? I mean, partial snapshot if there are only delta that is changing to just get the delta. Um, so we can create a custom schedule. We can specify how many times we want to schedule this, and all this can be programmatically invoked, can be programmatically configured through the workflow based on the use case. And then you can specify the devices that are in reference here. And then once you have set up the collector has generated the snapshots. So you can see here, so the collector would operate on a nightly basis, would generate snapshots, would have similar to how NSO has all the data, live network configuration data in its CDB. In its device model, forward network, forward platform is able to capture the snapshot of it. And if there is a snapshot that's already being captured, we can import the snapshot as well. And if there is if there is a snapshot that we no longer want to use, we can delete that as well. So having said that, so let's go do a Google like search. So we want to go from a source to destination, right? We want to be able to translate the intent of a request, and then want the engine, the BP engine, to be able to make these decisions. So let's say we want to go from like a firewall to another. Uh, so I'm just going to pick. So as we can see, there are three possible paths here. I'm going to expand upon that. So there are three possible paths that are listed here to go from ATLC01 to ATLC02. And you can see the forwarding. You can apply filters based on the forwarding behavior, based on the list of devices that are in reference here. So this is a sum of all devices in the entire path. Um, and then you can also filter based on your interfaces and the packet headers. So if you click on the device here, you can see a sample packet. So you can see the device state. So let's go take a look at the sample packet. It has the IP address, the source, destination. You can transcend within this path, so from one node to another, and determine which are the active links, which are having missing links, what is the usage, and you can have custom tags attached to each of these nodes. Say, for example, in this diagram that we are looking at, in this first path, we can define metadata which says, hey, ATL-C01 is from internet. ATL Edge FW01 is from a management network, and then ATL C02 is within production. And based on that, like, we are able to get the whole path. We are able to get the metadata corresponding to each of these nodes, and we are able to say, hey, we are originating from internet. I'm going to production. So that is critical. So that is red. So we kind of have to flag that as red, and there are appropriate device configurations that would need to be added because it is deemed to be red. So you can select, you can examine the return path as well. As you can see, the packets are being dropped here. You can see the return path for some of these use cases. So what would involve is, like, so there is a decision that needs to be made. So we have three different paths that are available. How do we zero in on a path among the three different paths that we see here? So that's where business logic is necessary. That's where it will be more applicable for this to be consumed by, like, a northbound system like a BPA that would kind of help you drive as to why you need to select this path over the other.
Quick time check. We're at 3:48. I don't know if you want to save a few minutes for questions.
Sure. Thank you. Yep. And another thing I would like to show is the state here, right? So you can look at the you can filter based on what kind of headers you are looking at, devices, or the forwarding behavior. And any questions on the platform based on the demo before we kind of go back to formal Q&A? Okay. Um, okay. Okay. So just to quickly summarize, NSO offers the best configuration management capabilities for multi-vendor networks, be it the firewall, routers, switches, load balancers. Path analysis platforms such as an example that we saw today. There are other examples. Facilitate intent-based network path analysis and topology diagramming with some very valuable metadata when it is able to consume this live snapshot, network snapshot, or configuration data. Interoperability between NSO path analysis tools using OpenConfig standards bolstered by BPA would be very symbiotic. It would be able to unleash enormous value for customers for end-to-end intent-based business process and network automation. If you want to reflect our discussion today on intent-based network automation in a single phrase, I would say path analysis. In two phrases, I would say Cisco BPA and Cisco NSO-driven path analysis platform. So, if there are any questions?
All right, with that, let me go ahead and get a microphone. Okay, with that, any questions for Krishna? Okay. All right, Krishna, I don't see any questions. Have you last words?
Yeah, I think what we have done today is just to scratch the surface with one approach to facilitate intent-based firewall automation. There are other approaches. We just picked up an example with the Forward app. So what we are looking at is essentially the algorithm, the approach, and being able to take the best of NSO's configuration management capabilities, and then path analysis platforms, ability to make inferences, make interpretation of the data that it is able to consume from NSO. So I think as we keep evolving, I think we will start seeing more value to end-to-end customer business process.
Krishna, looks like we do have one question. We bring it out. And actually, we do have time. Okay.
My question is, to discover the topology, do you need some database of the devices, how they are connected, or you fully discover the topology?
Fully discovered, I've missed the last part.
So to discover the topology, do you need some inputs, like the devices, how they are physically connected, or you fully discover the topology without needing any inputs from any database?
Right. So what it does is, like, it is when the data collector collects the device, does the data collection, it needs the capability to be able to SSH to the device. It collects the forwarding tables, the routing tables, and it uses various protocols, BGP, OSPF, to gather the routing tables, and then analyzes the space of packets from different routing tables, and is able to make that inference. So to answer to your question, in addition to providing the list of devices and providing credentials for the Forward platform to connect to the devices, do we need to provide any inputs regarding the links? No, we don't. But it needs to be, if there is a new link that's added, it needs to be captured by the next data collection. If it was not captured in the previous iteration of data collection, Forward would not be able to recognize that. But if it is a new link, and when it is doing the data collection in its next iteration, it will be able to discern that and be able to take that into its topology. What we saw as a topology tree diagram, it will be able to load that into the topology tree and be able to handle that.
Thank you.
Sure. Okay. Anybody else? Okay, if not, two things. First of all, thank you, Krishna, for a presentation. Give him a round of applause.
Thank you.
Cisco, the bridge to possible.